All right, hello everybody. We're going to be getting started here in just about 2 minutes. Still have a lot of people trickling in, but we are here and ready to go, and we will be starting in about 2 minutes. All right, everybody, thank you for joining us. This is the Advanced SKYWARN Spotter Training. My name is Jim Sullivan. I'm a forecast here at the National Weather Service Forecast Office in Cleveland, and I'll be taking you through these slides here over the next couple hours, and we'll have about a 5-minute break worked in about halfway through because it is a pretty long presentation. So we'll jump right in, and the big difference between this training and the basic training, if you've taken the basic training, is this just goes a little bit more in depth into what we'll call the why, if that makes sense, kind of what drives some of the things that we see with severe thunderstorms that you may be seeing out there as spotters. So a little bit more about our office here. Our main mission is to protect life and property. And SKYWARN spotters who report things like damaging winds, large hail, tornadoes, or flooding to us are a vital part of that because that helps us create better warnings and helps us relay to people, in the path of the storms, what the storms themselves are doing. So there's about 25 of us that work here at the Cleveland office, 14 forecasters like myself. We also have several electronic staff and IT personnel, some administrative people. We have a hydrologist, an office assistant, and an observation program leader. So it all adds up to about 25 people. We are here 24/7, 365, and we issue warnings for things like tornadoes, severe thunderstorms, floods, and any other hazard weather-related that you can think of. So there are 122 weather forecast offices just like ours across the United States and in the US territory. So there's an office in Puerto Rico, Guam, and even the American Samoa, along with the lower 48, Alaska, and Hawaii. And here's what our operations floor looks like. We have 8 workstations plus a 9th in the middle. We have a situational awareness display in the background there. that shows webcams and observations from across our area. And so it's a pretty big office space, and we just moved here a little over 2 years ago in 2020. We were at Cleveland Hopkins Airport for a long time before then, but now we're in Brooklyn Heights, Ohio, pretty close to the intersection of I-77 and I-480. So this is the area that we cover. We have 30 counties in our forecast area, or what we call our county warning area. This is the technical term for it. And about 5.5 million people live in this area in several larger cities, including Cleveland, Akron, Canton, Youngstown, Erie, and Toledo. And some of our southern counties there south of Mansfield are kind of pushing into the Columbus metro area as well. So we cover quite a bit of real estate, and we also cover a large portion of Lake Erie. We produce river forecasts for a couple of dozen river forecast points across those 30 counties. We produce forecasts for 7 of the airports across our area, the larger ones. We also maintain a number of climate stations, weather radio stations, and we have 2 radars in our area. We have the classic K-CLE radar. That's the common radar that if you turn on the news, they're probably showing you radar data from that radar. But we also have a terminal radar maintained by the FAA out near Oberlin, which helps us out a little bit. And as I alluded to earlier, we're in parts of 5 television markets. Obviously, Cleveland is the central one, but we have several more completely or partially in our CWA or forecast area. So again, here we maintain a weather watch 24/7 and issue all of the weather-related watches, warnings, and advisories. And that's kind of like the key thing that we do here day to day is issue forecasts and warnings. But on top of that, we're always building relationships with local governments and emergency management and providing advice to a lot of these folks. And we're always looking for customer feedback from our end users and trying to kind of get better and serve you and everyone else we work with the best we can. So here is our contact information online. Our website is www.weather.gov/CLE. We're also on Facebook, Twitter, Instagram, and YouTube. And I would say Facebook and Twitter are where we're most active, at least on a day-to-day basis with forecasts and weather information. So diving now into the talk, it's a little bit about us. We're going to start with thunderstorm ingredients. What do we look for when we're trying to figure out if there will be thunderstorms and potentially severe thunderstorms? So give me just a second. So, there's a few things that we really look for. We need an unstable atmosphere or instability. We need enough moisture to get those large thunderclouds to develop and produce rain and hail. We need some sort of what we call lift to make the air start rising. That's how you get a thunderstorm to start. And severe thunderstorms in particular also need wind shear, and we'll get into all of these things here. So the first ingredient, you need some amount of instability in the atmosphere to get a thunderstorm to develop. And the most basic thing here is hot air rises. So most of the time that hot air just comes from the sun heating up the ground, which then heats up the air directly above it. And that causes the air at the bottom of the atmosphere right at the ground to be much warmer than the air above it. And since warm air wants to rise, that causes instability. So basically, the larger the temperature difference between the ground and the air above, the greater the instability. And this is why, say, in winter, we get lake effect snow, because the air above the lake might be 15 or 20 degrees, and the lake early in the season might be 40 or 50 degrees. So that's quite a bit of instability. We're obviously focusing on more summertime thunderstorms here. So instability is maximized on days where it's warm and sunny. That's why a lot of times when we get severe weather, it's actually a pretty nice day until the thunderstorms come around. And that's also why a lot of times if it's kind of a rainy, showery day, we can struggle to get severe weather later in the day because we don't have that sunshine heating it up. And it also helps if it's abnormally cold aloft, and that cold air can come from a disturbance or a front moving through. It can come through air blowing in from different parts of the country, which we'll get into shortly. So Basically, a couple of definitions here. Stability, the degree to which vertical motion is enhanced or suppressed when an air parcel rises. So to boil that down, it's considered stable if the atmosphere is actually suppressing rising motion, and it's unstable when the atmosphere is encouraging rising motion. So the most simple way to measure this is how quickly temperature changes with height. And this is because when air rises, it cools at a set temperature, the rising air. So when saturated air rises, it cools at what's called the moist adiabatic lapse rate. That's a big word, but basically that means that saturated air, when it's rising, cools approximately 6 degrees Celsius for every kilometer it rises. And a air parcel, and when I say air parcel, I just mean a chunk of air. So fancy way of saying a chunk of air. When a dry chunk of air rises, it cools at 9.8 degrees Celsius per kilometer. So we know how quickly a saturated or unsaturated parcel or chunk of air is going to cool as it rises. So we look at the rest of the atmosphere and look at how quickly it cools to determine if that rising parcel will end up being warmer than the surrounding air, which means it's unstable, or cooler than the surrounding air, which means it's stable. And the reason this makes it stable or unstable is a warmer air parcel compared to the surrounding air, it'll be less dense than the surrounding air, so it will want to rise, it'll be buoyant. Whereas if that air parcel that's rising is cooler than the surrounding air, it's denser, it's heavier, and it will not want to rise, so it's very stable. So an unstable air mass is what we're looking for thunderstorms, and we can kind of determine very simply if it's stable or unstable based on how quickly the atmosphere is cooling with height, and we can compare that to the moist adiabatic lapse rate and the dry adiabatic lapse rate. So one way that we can get, very strong, what we call lapse rates aloft, which means the atmosphere is cooling very quickly with height, which can lead to very strong instability, is what we call an elevated mixed layer. So if you think back a few slides, we said a big way to get instability is for the sun to heat the ground, which then heats the air above the ground. And let me go back, and we have all these mountains in Western North America stretching all the way from Canada across the Western United States into Mexico. And when the sun heats the air above the mountains, it heats the mountains and heats the air above them. It creates a layer of instability above the mountains that then blows east where there's lower terrain towards our area. And when you get that mid-level air that's been kind of heated and modified and made unstable over the higher terrain to the west, and it blows east, it can blow east over top of very moist air that's moving northward out of the Gulf of Mexico. And getting that combination of warm, moist, humid air in the low levels and an elevated mixed layer in the mid levels can result in a very strong amount of instability. It's what we call an elevated mixed layer when this happens, and this maybe happens a couple or a few times per season here on average, where we get a true elevated mixed layer that makes it this far east off of the Rockies. But when that does happen, that tends to be associated with some of our more prolific severe weather events locally. We'll discuss this later, but the derecho event that we had last summer, last June, went across quite a few of our southern counties, especially it hit kind of the Mansfield, Millersburg area very hard. That occurred in the presence of an elevated mixed layer. So another way to truly quantify instability is what we call, the measure is called convective available potential energy, or CAPE for short. And this is a more direct measure of, we kind of look at the temperature of a rising chunk of air or air parcel all the way through the atmosphere, and we compare that temperature to the temperature of the atmosphere and calculate how much instability exists through the whole atmosphere between the two. So here's some very rough guidelines that we look at least this time of year as we head into the summer, for how much CAPE tends to be associated with thunderstorms and severe thunderstorms. and also a theoretical maximum updraft strength based on the cape. So that's just calculated based off of how much cape is available, theoretically how quickly an updraft could be rising based on that amount of cape. So generally, if we're looking at 500 to 1,000, the units for cape are joules per kilogram, but we'll just stick with the number. If we're looking at 500 to 1,000 cape, that usually indicates to us that we can get thunderstorms, but probably not severe. 1,000 to 2,000 is where we start looking at severe thunderstorms becoming more likely. And more than 2,000 joules per kilogram of cape, that's a pretty significant amount of cape. And that's when we start seeing most of our major severe weather outbreaks. So there are some advantages and disadvantages to cape. It's easy to calculate and widely available, and everyone in our field looks at it, and it's a good first guess, but there's some key things to remember. P is potential. So there are ways that sometimes we don't tap into the cape. Sometimes there's just no lift in the atmosphere. So there's nothing to get the air rising in the first place, so the cape doesn't really get used. And that might be common on just a hot, humid summer day where there's no weather systems to really spark thunderstorms to develop. So you may have the cape on those days, but you don't get many storms. And in winter or early spring or late fall, we'll call it the cold season, between about October and April, the weather systems are just very strong, and you can get thunderstorms with relatively low amounts of cape that time of year. These numbers are more applicable, I would say, in the late spring, summer, and early fall months. So there are some different flavors of cape, and we won't spend too much time on this, but these are things that we look at when we're trying to forecast severe weather potential and if storms will develop. Because storms, most commonly, they form from air near the ground that's rising up, and that is where surface-based cape, which is the cape of what we call an air parcel originating from the ground, or mixed layer cape, which it kind of takes an average air parcel in the lowest few thousand feet and calculates the cape off of that. Those are our most common two capes for, your kind of run-of-the-mill afternoon, evening thunderstorms. But there is another element or another type of cape called most unstable cape. And that might help us evaluate thunderstorms that develop maybe in the middle of the night when maybe the air that's causing the thunderstorms is originating above the ground, or even during the day if it's cold near the ground, but we're still getting thunderstorms. Sometimes it can be cold near the ground, but you get a warmer layer above the ground, and it's that warmer air above the ground that's unstable. Those are what we call elevated thunderstorms. So these are the three different flavors of cape. We won't talk about these too much more, but if you really get into the weeds and maybe read some of the technical discussions that the Storm Prediction Center puts out or that our office puts out, you may see these different capes referenced, and that's just what it means. But we won't spend too much more time dwelling on the different types of capes. So moisture is needed for thunderstorms. So if it's a very hot and very dry day, you're probably not going to get a thunderstorm. You do need some amount of moisture. Why? Well, first of all, you need moisture to form clouds and rain and hail. That's all moisture that's getting squeezed out of the atmosphere. So if you don't have it, you're probably going to have a hard time getting a thunderstorm. And also, moisture increases instability. We talked about this a little bit earlier. When saturated rising air condenses, it gives off a fair amount of heat. When clouds develop, it gives off a pretty good amount of latent heat and actually warms the rising air parcel compared to the environment. So rising saturated air tends to be more unstable than rising dry air. And then that's another reason why we need a fair amount of humidity usually for good thunderstorms. And a quick and dirty way of kind of measuring total atmospheric moisture is what we call precipitable water. And that literally just takes all the water in the entire atmosphere and says, okay, if all this water were to rain out right now, how much rain would it be? So basically, the higher the precipitable water, the more moisture in the environment. And again, you may see this referenced if you read some more technical discussions occasionally put out. But once we're getting near or more than 2 inches of precipitable water, that is a very humid environment, and that starts indicating increased flash flood potential. Most of our typical thunderstorm days have maybe 1 to 2 inches of precipitable water in the atmosphere. So dew points and relative humidity, we'll touch on this. Dew point is how humid the air is at the surface, and relative humidity, as the slide says, it's just that, relative. So relative humidity can change quite a bit depending on the temperature, whereas dew point is an absolute measure of moisture at the surface. So an example of relative humidity, if the air temperature is 40 degrees with a dew point of 40 degrees, that is a 100% relative humidity. You're probably not going to be walking around going, wow, it's really humid out here today because it's 40 degrees and the dew point is 40 and it's not that humid. It's not a hot and humid summer day. Whereas if it's 95 degrees with a dew point of 74, you are going to walk outside and immediately sweat and be like, oh my goodness, it's awful out here. It'll feel very humid. That's only a 50% relative humidity, whereas opposed to the prior example, a 40-degree dew point on a 40 degree is 100% relative humidity. The dew point of 74 is what you're really going to feel. So dew point is an absolute measure, whereas relative humidity is very tied to the temperature. And nice little graphic there on the right. Once you get dew points rising through the 60s and into the 70s, it quickly starts feeling more uncomfortable. And we typically look for dew points near or more than 60 degrees when we're trying to look for environments conducive for severe thunderstorms, especially in the summer. As I mentioned earlier, in winter, when we get much stronger weather systems, sometimes we can get severe thunderstorms with much lower dew points. But in the summer, we generally look for 60 or higher. So moving on through the thunderstorm ingredients, we need something to get that air rising. It's what we call lift. And so what are ways to get air rising? What are some sources of lift? The most common are cold fronts and warm fronts, mountains, or even smaller hills. Air blowing over those inherently has to rise, so that can be a source of lift. Commonly around here, especially in the summer months, we can get a lake breeze along the Lake Erie shoreline. That can be a source of lift. And old thunderstorms can be a source of lift, because sometimes when you get thunderstorms that dissipate, they leave wind shifts or little boundaries, and those can act as sources of lift for new thunderstorms. So the impact of terrain here in northern Ohio into northwestern Pennsylvania is relatively small. Here's a topographic map centered on our forecast area. So the storms moving up these hills, sometimes they can intensify a little bit just because there's some inherent added lift as the storms move up the hills, and maybe they can weaken a bit as they move off the hills. But in the grand scheme of things, our terrain has a pretty minor impact on our severe weather. We've had severe weather on top of our hills and in our lower elevations. And just for some perspective, we turned up the color scale on this map just to make our hills pop a little bit more. But along the Lake Erie shoreline and in northwest Ohio, where we have lower elevations, we're sitting somewhere around 600 feet in elevation above sea level, give or take. And our higher elevations located near Mansfield and in Geauga County, and then especially in northwest Pennsylvania, our higher elevations in Ohio are 1,000 to 1,200 feet. And in northwestern Pennsylvania, we do have some hills that are pushing 1,500 feet, but it's not a ton of elevation change across our area. Definitely not the Rocky Mountains or anything like that. So overall impact from terrain is small, but sometimes as storms move up those hills from west to east across our area, we see them get a little bit of a kick. But that's about the extent of it. So here's a good example of how it can be complicated trying to figure out what's going to cause thunderstorms to develop. So this is a surface map from the Great Plains, some random April day in 2020, and that blue line with triangles, that is a cold front on the surface map, so your standard cold front. And that dashed kind of gray, or not gray, more of like a tan or orangish brown line in front of it, that's what we call a prefrontal trough. And in this instance, the prefrontal trough is actually what caused the storms to develop for the most part. And you'll see that on the satellite loop. It'll loop through again, but as you go towards the loop, notice how the storms really blow up in like Missouri, which is along the prefrontal trough, as opposed to the cold front that's just coming into Iowa. There were a few storms along the cold front, but in this case, it was the prefrontal trough that really did the heavy lifting, so to speak. So that's kind of a common question for us around here, because it's not uncommon that we have a cold front coming in, but we have little wind shifts, or what we call a prefrontal trough, in front of them. And the big question for us is, okay, which one of those sources for lift is actually going to cause the storms to develop? And sometimes it's one or the other, sometimes it's both, and it gets very messy. So moving on from lift, another pretty important ingredient for especially severe thunderstorms is wind shear. So there's a couple different flavors of wind shear that can be important. One is what we call directional shear, and that is when the wind direction changes as you go up in the atmosphere. You might have winds near the ground out of the south or southeast, and winds up at the jet stream level at 30,000 feet out of the west or southwest. So you can get quite a bit of turning over the course of the atmosphere. And the other flavor of wind shear is speed shear, and that is just wind speed changing with height. So the most conducive type of shear for severe weather is when you get speed shear, wind speeds increasing with height, and also some amount of directional shear. Having both of them is what we usually have in place when we do get rotating thunderstorms that might produce tornadoes. So why is wind shear important? Well, if you don't have wind shear, what happens is the thunderstorms go up, you get all that warm, moist, humid, unstable air rising, but then you get the rain-cooled air falling out of the thunderstorm right on top of the warm air that's getting sucked into it, and it basically chokes off the thunderstorm and causes it to dissipate pretty quickly. And this is what, these are your popcorn thunderstorm days in summer, where you look at the radar and you just get little cells popping up and quickly dissipating. That's usually because the wind shear is low. When wind shear is higher, what happens is the rain-cooled portion of the thunderstorm is separate from the warm, moist, humid, unstable updraft. And since the cold air is kind of separated from the storm's fuel source, the storms can last much longer and become more intense and usually more severe. So a layer that we typically look at for wind shear in thunderstorm environments is the surface to 6 kilometer above ground level layer. That's a pretty common layer that we look at when we're assessing how much wind shear there might be for thunderstorms. And again, the more wind shear, usually the more favorable it is for severe weather. And when we're looking at squall lines, the amount of wind shear available can determine how intense squall lines are and how long they last. And the reason for that is when we get clusters or lines of thunderstorms, if you think of when a line of thunderstorms hits your area, if you're, maybe if you have the windows open or if you're outside, when thunder roars, go indoors. I wouldn't encourage you to stand outside when thunderstorms are coming in, but you've probably noticed it at one point or another. A lot of times when a line of thunderstorms comes in, you get a big cold gust of wind. And that's because the thunderstorm has what we call a cold pool. And that happens just from all the rain-cooled air descending out of the thunderstorm and getting to the ground. And it over time can build into a pretty large area of cooler air. And that cold, dense air near the ground has a urge to kind of rush out ahead of the thunderstorm. And if there's no shear, as we can see on the top, what will happen is the air will rush ahead of the thunderstorm quicker. The thunderstorms will be a little bit tilted back above the cold air. They won't be as tall, and eventually they'll get cut off by the cold air running out ahead of them. But if there is more wind shear, we get better balance between the cold pool and the thunderstorms themselves. The cold pool doesn't want to rush out as far ahead of the thunderstorm. The thunderstorms are a little bit more vertical, so they're taller, more intense, and they tend to last longer. So even with squall lines, the right amount of wind shear can make a big difference in terms of how severe a squall line ends up being. And we won't spend a ton of time on this because this is really getting into the weeds, but low-level wind shear, both speed shear and directional shear, are important to getting rotating thunderstorms. So this plot here, we won't get more into the weeds than this, but this is what we call a hodograph. It is something we look at every time we are assessing here at the office potential for severe weather. And basically the hodograph plots with height the wind speed and direction through the atmosphere, and then it also plots the storm motion. And this is really getting into like Calc 2 level math here. But basically the area under the curve is a value that we call the storm relative helicity, SRH for short. And basically the more SRH there is, the more potential for a rotating thunderstorm and potentially a tornado there is. So we won't get into this more than that, but just know that there are ways we quantify the amount of wind shear. We're not just sitting here looking at maps and going, oh, it looks like there's a lot of shear today. There is a lot more math behind it than that. But yeah, more helicity tends to support rotating thunderstorms, what we call supercells, and potentially tornadoes. So, kind of boiling all this down, the amount of wind shear and the amount of instability can kind of help tell us how storms are going to behave on a certain day. So, we touched on this a little bit, talking about the ordinary cells, and I believe we'll talk about this more on the upcoming slides. An ordinary cell is just your regular popcorn thunderstorm. Multi-cells, that can cover any sort of organized thunderstorm system, or convective system as we call it. Anything from a cluster of thunderstorms to a squall line is what we would categorize as multi-cell. And then supercell, that is a rotating thunderstorm. And supercells tend to be the most prolific hail and tornado producers. So again, we don't want to put anything, I don't want to box everything in here, but generally if there's less than 25 knots of shear, on the left-hand side of this chart, we're looking at ordinary cells, maybe with a little bit of organization and maybe some isolated severe weather if there's a lot of cape, a lot of instability. And then once we get towards more shear, 40 or more knots, that's usually when we're almost exclusively going to have multi-cells or supercells. And the more instability you have to go along with that shear, the more intense and organized and severe the storms may be. And some days we can get both multi-cells and supercells at the same time. So again, it's hard to box things in. These are generalized, but in general, the more shear and the more instability we have, the more organized and severe thunderstorms will be. So another plot that we can look at to really quantify all of this, and this is something we look at again every time we're forecasting thunderstorm and severe weather potential. This is what we call a SKYWT. We'll go through it really quickly. The red line is the temperature of the atmosphere as you go up in height. So you start at the surface, and then this plot goes up to 100 millibars in height. That is into the stratosphere. So that's like 50, 60, at least 1,000 feet up. So this is the temperature through that entire depth of the atmosphere. The green line is the dew point temperature. So the closer the red line and the green line are together, the more saturated the atmosphere is, the more humid it is. And then on the right, we have winds with height, and the wind, the kind of the back or the pointed end of those, like, you kind of get the flags or the lines on one end and then a line on the other. The line kind of points towards the way the wind is blowing. So at the surface, the wind is coming from the west-southwest at the bottom of this plot and blowing towards the east-northeast. So we would call that a west-southwest wind. And then this dashed white line, we talked earlier about when you get air parcels or chunks of air that are rising through the atmosphere, they cool at a very set rate depending on if they are saturated, a 100% humidity or not. And so this calculates how the temperature of a rising air parcel. And if you notice at the bottom of the chart, that dashed gray line is cooling very quickly, and that is because down there, that rising air is not yet saturated. So it's cooling quickly, But then at about this first line here, about 5,000 feet up at 850 millibars is what we call that, it becomes saturated and it starts cooling slower. So you can kind of see the different lapse rates we have to consider. And then you kind of compare the temperature of the rising parcel to the temperature of the atmosphere, and you get the total amount of instability, or CAPE is the area between those two lines. So these are things that we look at, and in this case, there isn't a whole lot of wind shear because the winds are all blowing from the same direction, and they're not very strong as you go up through the atmosphere. So a pretty low amount of shear here, and here's a link to, on the Storm Prediction Center's website, some real-time observed soundings. We do not launch weather balloons that collect these soundings out of Cleveland, but several surrounding offices do, including Detroit, Wilmington, Ohio, and Pittsburgh, and even Buffalo does. So a lot of our surrounding offices launch weather balloons that measure all these things. So to kind of sum up everything we've gone through so far, the ingredients for severe thunderstorms, we like our acronyms here in the weather community. So we're going to create an acronym here called the SLIM ingredients for severe thunderstorms. You need some amount of shear, at least for severe thunderstorms, lift to get air moving up, instability so that upward moving air continues rising, and moisture, or else you're not going to get your clouds and rain and thunder and lightning that you get with a thunderstorm. So these are the ingredients we look at for severe thunderstorms, and now we're going to start diving into how all these ingredients work together to produce thunderstorms and severe thunderstorms. So the most critical, kind of the starting point for a thunderstorm is what we call an updraft, and that is the portion of the thunderstorm where all that warm and humid and unstable air near the ground is getting pulled into the thunderstorm and rising, and it's basically the fuel for the thunderstorm. So if you're ever looking at a thunderstorm coming in, a lot of times what you can see is you can see part of the thunderstorm where the clouds look really, really dark and scary and mean, but there isn't any rain coming out of them. And then other parts of the thunderstorm, you can see the buckets of rain literally pouring out of it. That base of the clouds where rain isn't coming out of, that's usually where the updraft is, because the air is moving up so quickly that the rain doesn't fall through it, at least initially. So that's one way to find an updraft if you can ever actually get a good look at a thunderstorm moving into your area, is you look for the portion of the clouds that look, pretty menacing but don't have rain coming out of them. That's usually where the updraft is. And then what goes up must come down. The downdraft is the portion of the thunderstorm where rain and hail and rain-cooled air come rushing towards the ground. And once they get to the ground, they begin flaring out. So it does take some amount of time for downdrafts to develop. Once you get an initial updraft, you need an updraft to usually persist for at least 10 minutes for precipitation to begin developing aloft. Hydrometeors is just a really fancy word for precipitation particles. So raindrops, ice crystals, snowflakes, hail, those are all hydrometeors. At a certain point, the hydrometeors, they are heavy enough and there's enough of them that they begin rushing towards the surface. And, sometimes these downdrafts can begin accelerating on their way to the ground. If there are layers of dry air in the atmosphere that the thunderstorm is interacting with, dry air aloft can actually help downdrafts speed up towards the surface, and we'll get to this later, but that could increase the risk for damaging winds. And the reason this happens is when you blow dry air into a thunderstorm, the thunderstorm is obviously full of moisture, but that dry air getting blown into it causes evaporation to start, and evaporation is actually a cooling process, and that can cause the air aloft in the thunderstorm to become colder than the surrounding atmosphere, and that can actually cause the downdrafts to speed towards the ground, and that can result in damaging winds. And we'll get to that more later. A shelf cloud is something that you might see on the leading edge of a thunderstorm, kind of on the interface of the updraft, or of the updraft and the rain-cooled air. So I'll go back a slide real quickly. So this is a schematic of your garden variety thunderstorm, and you see the updraft in red, where the warm and humid air is getting pulled into the thunderstorm. You see the downdraft in the blue, where the rain-cooled air is falling towards the surface, and then you see a line near the surface. It's kind of looks like a cold front on a weather map. That is what we call the gust front, and you can picture the rain or the updraft, the warm humid air kind of getting lofted as it runs into that gust front. So a gust front surging out is actually how shelf clouds form, because the rain-cooled air surges ahead into the warm, humid, unstable air, and it causes the warm, humid, unstable air to rise into the shelf cloud. So a shelf cloud, they are very interesting to look at, very picturesque, but they aren't usually associated with anything tornadic. It just shows where that rain-cooled air is rushing out of a thunderstorm. So shelf clouds, a lot of times they can be accompanied by a nice gust of strong wind along the gust front, and sometimes thunderstorms dissipate, or maybe the shelf cloud just rushes out ahead of them, and when that happens, the shelf cloud turns into what's called a roll cloud, where the low portion of the cloud persists, but it's not attached to a thunderstorm anymore, so it can look really interesting, but it's nothing severe. It's just called a roll cloud. So sometimes you can see a lot of motion in a shelf cloud. You might see some rising motion, you might see some turbulence, but you usually aren't going to see true tornadic rotation with a shelf cloud. So getting into the types of thunderstorms, your most basic type of thunderstorm is what we call an ordinary cell, or a single cell, or a pulse type thunderstorm. These are the thunderstorms that you get on your typical warm, humid day with very weak wind shear. A thunderstorm develops. It starts out just as a big towering cumulus cloud. It gradually grows into a thunderstorm, but because there isn't any wind shear, the rain-cooled air ends up falling directly on top of the updraft, and it causes the updraft to get choked out. The storm rains itself out. So that is an ordinary single-cell thunderstorm. Ordinary thunderstorms typically are the least likely to be severe, just because they don't last long enough and they aren't organized enough to really max out the intensity, or max out the potential instability in the atmosphere. They don't take full advantage. You can get some severe weather from an ordinary cell thunderstorm if it is unstable enough. Even though the storms don't last long, when it is really unstable, when there's a lot of cape, you can get maybe some brief hail. You might get a pretty good gust of wind as the thunderstorm collapses. So you can get isolated severe thunderstorms from these ordinary single cell pulse type thunderstorms, but in general, they are the least severe thunderstorms. Moving on to multi-cell thunderstorms. So once you start getting some amount of wind shear, it can start separating the upper portions of the storm, where all the rain-cooled air comes from the lower portion of the storm, where the updrafts get lifted into the storm. So once you get some wind shear, you can get, what we call multi-cell. So the least organized type of multi-cell is what we call a multi-cell cluster. So this isn't going to be your big squall line, your bow echoes, or anything like that. These are just kind of your clusters of thunderstorms that I would say are pretty common on a lot of our severe weather days around here. There's enough shear that they're more organized than the pulse or single cell storms, but they're not extremely organized or severe yet. Again, with multi-cell thunderstorms, you usually start getting an increased risk for damaging winds. And once you get really intense multi-cell storms, you can get some hail and even some tornadoes. So kind of moving on up, once you get, so the difference between kind of your regular cluster of thunderstorms or something much more organized, like a big squall line or a derecho, and we'll get into what a derecho is in the next couple of slides. The big things that can cause kind of that leap from a disorganized cluster to something much more organized is more wind shear, or a strong lifting mechanism like a big cold front. That is what turns your regular multi-cell cluster into a more organized squall line or potentially a derecho. So once we start getting squall lines, that's when we can start getting some pretty widespread wind damage from thunderstorms if the environment is conducive, and they can last longer, and sometimes they can turn into what we call a derecho. So what is a derecho? It's a term that's thrown around a lot, but it has a very specific definition. So a derecho is basically a long-lived thunderstorm wind event. And this thunderstorm wind event, it must have gusts over 58 miles an hour. So 58 miles an hour, that is the severe limit for wind. So a derecho must have severe wind along its entire length, and that length needs to be at least 240 miles long. And there need to be at least some wind gusts over 75 miles an hour at various points along that damaged swath. So what we have looping here in this image is a radar loop of a derecho that occurred last June 13th into the 14th. It impacted a good portion of our southwestern counties. It started here early in the loop over Wisconsin and northern Illinois. And with time, it grew into a much more organized squall line as it moved right across our area. And it produced wind damage along this entire length, and it produced very intense wind damage across parts of our area. So here's what the reports look like from that day. So just real quickly, early in the loop, there was a cluster of storms in southwestern Ohio that moved into West Virginia. That was not a derecho. It didn't last quite as long. And then this little cluster here developing at the end of the loop, that was in the middle of the night behind the derecho. It just wasn't as severe. It's this line taking shape right here. That was the derecho that did the bulk of the damage. And you can see as it moved across our area, it exhibited a bowing shape, which is a classic sign that thunderstorms are producing some very strong wind. So here were the reports from that. And the derecho followed this red line. So the cluster of storms that started out in southwest Ohio, it just wasn't quite severe enough to be a true derecho. But our derecho started in Wisconsin and northern Illinois, moved all the way across our area. So it lasted close to 400 miles. And there were numerous wind gusts over 75 miles an hour along that path, starting as early as over Wisconsin. There was a measured wind gust of 98 miles an hour in Fort Wayne, Indiana. And then in our local area, we had estimated wind gusts, well over 80 or 90 miles an hour in parts of Wayne, Holmes, and I believe Morrow and Knox counties. We estimated wind gusts over 80 miles an hour. So several well-separated gusts over 75 miles an hour that made this a derecho. So it's hard to know ahead of time if something will be a derecho, because there are these very stringent criteria that need to be met. And a lot of times we don't know until after the fact if it was a true derecho or not. So moving on from multi-cell thunderstorms, which again is kind of the catch-all from anything from a cluster of storms to squall lines and derechos, moving on from that to supercell thunderstorms. So as the name supercell implies, these aren't your regular garden variety, run-of-the-mill little thunder showers. These are, these mean business. So a supercell thunderstorm, it's just a thunderstorm that has a persistently rotating updraft. And supercells form in environments featuring strong instability and strong wind shear. So all supercells have a rotating updraft, and most supercells are severe. Supercells, because of their rotating updraft, as I mentioned early on, and when talking about ordinary cell storms, when the updraft and downdraft are on top of each other, it isn't conducive for a lot of severe weather, because the downdraft is full of rain-cooled air that will cut off the updraft. But with supercells, the updraft and downdraft stay separate, so they last longer. The updraft is rotating, which can make it more intense and can also contribute to tornadic development. So supercells are the most prolific large hail and tornado producers. With that said, only about 20% of supercells produce tornadoes. So when we're trying to figure out if we need to issue a tornado warning, Just having a supercell isn't an immediate yes, no. There is a little bit more that goes into it than that. So supercells can have updrafts that are blowing straight up at over 100 miles an hour, against gravity. So these things can mean business. And when you get those updrafts blowing at over 100 miles an hour, you can get very large hail to develop. In addition to that, the downdrafts with supercells can produce very strong winds, and a lot of times different parts of the supercells have downdrafts. And of course, supercells, because they're rotating, inherently have a risk for tornadoes. So kind of discussing the anatomy of a supercell a little bit. So this is an idealized diagram of a supercell. And the color fill kind of suggests what it might look like to you on radar. It shows where the precipitation is falling. So a few things here that are very characteristic of supercells that, we see these things on radar and it can tell us that we have a supercell. One is kind of the kidney bean shape with the hook on the southwestern side of a storm. So you might hear that we see a hook echo, and therefore it's a supercell. And a hook echo is a classic feature in supercells. But the updraft of a supercell, it tends to be located kind of in that red shaded area towards the bottom portion, the southwestern portion of the storm. That is where the warm, humid air is getting sucked into the storm. And that is partially what creates the hook echo on radar, is that updraft getting pulled into the storm kind of warps the precipitation around it. And then supercells have downdrafts as well, but they are separate from the updraft. And a lot of times supercells have two separate downdrafts. They have one on the leading edge of all the rain and hail, and then they have one on the trailing edge where air kind of rushes out and around the backside of the thunderstorm. That is called a rear flank downdraft. And, supercells are rotating, so you immediately think tornado, but even with supercells, these downdrafts can produce damaging non-tornadic winds. So when you get a supercell, again, it's not just the tornado to watch out for. It can produce large hail. It can also produce damaging straight line winds well away from any potential tornado as well. So rear flank downdrafts are interesting because sometimes the strongest winds in a supercell outside of a tornado are with the rear flank downdraft. And a lot of times there isn't a ton of precipitation with the rear flank downdraft. And also the rear flank downdraft can act as a source of lift for new thunderstorms to develop on. So supercells come in many different shapes and sizes depending on the amount of shear, the amount of instability, and the amount of moisture. But to make it really simple, every supercell has a rotating updraft, but they can present themselves quite differently based on all those other factors I just mentioned. The two most common types of supercells are what we call low precipitation supercells, where that's on the left, and you can see this is an idealized graphic, but you have the updraft on the left with the rain-free base that's very distinct, and you have some rain and hail falling out of it to the right, but it's not as much. And these low precipitation supercells are much more common in the central and maybe western United States, where they don't get as, they're just not as humid as we are. Usually around here, if we're seeing supercells, it's more of the high precipitation variety, just because usually it's a lot more humid around here when we're getting severe weather and thunderstorms and potentially supercells. So, if you're ever out and about around supercells, a key point here is, again, if a severe thunderstorm or tornado warning is issued for your area, we always encourage you to take shelter in a sturdy structure. But maybe if you are out viewing these from a safe distance, you just want to be careful with them, because supercells, they sometimes take on a life of their own just because they last so long, and because they're so strong, they can kind of alter the environment around them. So they can move erratically, they can split, sometimes they can dissipate pretty quickly, sometimes new cells can develop outside of old supercells, and sometimes they can produce lightning well away from where the actual rain is. So again, supercells, if you're ever out and about around supercells, be very careful with them and don't be complacent. And again, our advice always is to take shelter in a sturdy structure if a severe thunderstorm warning or tornado warning is issued. And the line always is when thunder roars, go indoors. So, moving on to some of the hazards that thunderstorms can produce, the big one is lightning. Every thunderstorm produces some amount of lightning. You cannot get light or thunder without lightning. So generally, the ground is relatively positively charged compared to the base of a thunderstorm that is negatively charged. So usually most lightning strikes occur from the bottom of the thunderstorm towards the ground, and they kind of work on fixing that imbalance between the positively charged ground and the negatively charged lower portions of the thunderstorm. And the way this charge builds up in thunderstorms is when you have those updrafts going from the warm, humid low levels to the very top of the thunderstorm where it is very cold, well below freezing, you have a portion of the thunderstorm where you have raindrops, snowflakes, hail, maybe some graupel, all intermingling in the updraft, kind of in the transition between the lower portion of the storm and the upper portion of the storm. And all those different hydrometeors, all those different types of hydrometeors rubbing up against each other in the thunderstorm is what causes this electricity to build up. Now, most lightning strikes are negatively charged, but occasionally you can get a positively charged lightning strike from the top portion of a thunderstorm. And positively charged strikes are a little more dangerous because they're a lot stronger because they work from the very top of the thunderstorm towards the bottom, towards the ground. So they have to travel a larger distance, so they inherently have to be stronger for that to happen. Also, because they kind of originate at the top of the thunderstorm, they can strike well outside of where the heavy rain is occurring. So a way to know that there's a positively charged lightning strike is, every once in a while you get that rumble of thunder that lasts a lot longer and it completely shakes the house or building that you're in, and you can almost feel it. That's usually because that's a positively charged lightning strike, whereas your more normal thunder is coming from a negatively charged lightning strike. So what makes a thunderstorm severe? Not lightning. So just because a thunderstorm is severe doesn't mean there isn't a risk of lightning. We look for winds greater than or equal to 58 miles an hour, which is 50 knots, nautical miles per hour, hail greater than or equal to 1 inch in diameter, and or a tornado. That is what makes a thunderstorm severe. So lightning or flooding don't necessarily make a thunderstorm severe. So again, even on your garden variety thunderstorm days, you need to be mindful, especially of the lightning. So how does hail form? Hail forms when you get what we call an embryo. So that's just kind of a chunk of ice, maybe snowflakes or graupel that form in the upper portion of a thunderstorm, but that is something that super cooled liquid water that's getting blown up through the thunderstorm's updraft can collect on. And as that super cooled liquid water collects on that embryo, it begins forming hail and it begins growing. And if the updraft is strong, it will keep that hail suspended for quite a long time and let it grow to a pretty large size until it gets too heavy for the updraft to support it, and then it falls towards the ground. Most hail forms or grows between minus 10 C and minus 30 C, that's Celsius. That's where hail develops. So that's between about 15 degrees Fahrenheit and about minus 10 degrees Fahrenheit. In a thunderstorm, that's where the bulk of the hail develops. And again, you need the hail to last in that cold air for a decent length of time for it to get large enough to reach the ground and as quarter-sized or 1 inch in diameter or larger. So kind of here's a little animation of how that goes. The super cold liquid water collects on the embryo, forms a new layer of ice, and the hail grows larger, and this process can continue for quite a long time when you get large hail. And so here's some pictures of how big hail can get. And you can kind of see, if you ever cut open a hailstone, a lot of times you'll see hail from the different layers of supercooled water that collect on it. And a lot of times hail is spiky just because it does not grow uniformly in the very turbulent and chaotic upper reaches of a thunderstorm. And it is, it's very rare around here to get hail this big, but, out in the plains, hail occasionally can be softball size or much larger. That bottom left image there, that is a 8-inch diameter hailstone, so massive. But more locally, we can get respectably large hail. It's not as common as out in the plains, but we can. Here's some pictures just from the last 15 years or so. Akron, Ohio saw, not pictured in this picture, but they saw hail softball sized out of this storm in June 2007. Last year out in Geauga County, we had a storm produce 2-inch in diameter hail, which is enough to really leave a mark. So, proof that we do occasionally get large hail in our area. 1 inch is considered severe. That's the point where you can start denting your siding, damaging your roof, dinging your car, and damaging vegetation. And once you get 2 inches in diameter or larger, you can get very significant damage from hail, especially if it is wind driven. Speaking of winds, straight line winds, so non-tornadic winds, are the most common type of severe weather that we get here in northern Ohio and northwestern Pennsylvania. And we touched on this a little bit earlier. Straight line winds kind of occur from that rain-cooled air and a downdraft rushing towards the ground and then spreading out when it hits it, and also the transport of stronger winds aloft towards the ground. So a lot of times, you might have 10 or 20 mile an hour winds at the surface, but you have 60 or 70 mile an hour winds somewhere in the upper levels of the atmosphere. And that strong downdraft, not only does it crash to the ground and then spread out with quite a bit of force, but it will push that stronger wind aloft towards the ground. So downdrafts are very important to getting damaging straight line winds. Usually straight line wind damage occurs all in one direction. The air rushes out of the thunderstorm in one direction. And sometimes you can get straight line winds that rush out ahead of the rain. And we talk, especially when wind shear is weaker, we talked about that earlier. And that is how sometimes you get a big rush of wind that sometimes is damaging before the heavy rain starts. So again, downdrafts are pretty much the origination of any straight line thunderstorm wind, and they develop when rain-cooled air aloft begins rushing towards the ground. And this is very hazardous for aviation purposes. Pilots will avoid thunderstorms because the downward moving air in a downdraft can crash an airplane. It's done it before, but the wind speed that results in thunderstorms is typically the result of a combination of how strong the downdraft is and how quickly the thunderstorm is moving, which is a sign of how strong the winds are aloft. So faster moving thunderstorms tend to produce more wind, but also thunderstorms that develop on very warm, humid days with colder air aloft, they tend to have stronger downdrafts, so they produce stronger winds as well. So the most severe winds occur on days where there's a lot of instability and where it's cold aloft and where there is a lot of wind aloft and everything kind of works together. So here is an idealized simulation of a downburst. This is, the cooler the color, the colder the air, and this simulates the rain-cooled air falling out of a thunderstorm towards the ground, crashing towards the ground, and you note how when the rain-cooled air hits the ground, it quickly spreads out, and that is kind of your gust front developing, your damaging winds beginning. And on the next slide, if I can get us there, Here's an example of this in the real world. This actually came from, I believe, Arizona, so they can occasionally get severe weather out there as well. Let's see if we can get this to play. Maybe. Come on. There we go. So you can kind of see there's your rain-free base initially where the updraft is, but then the downdraft kind of develops and takes over. And at a certain point, right around now, you see that rain-cooled air just crashing towards the ground. And then when it hits the ground, it quickly spreads out. And that is your downdraft rushing towards the ground and then hitting the ground and spreading out in what we call a microburst. And this loops through a couple of times, but this is a pretty dramatic example, but this happens in most thunderstorms to some extent. The trick is getting a strong enough downdraft that the wind at the surface when the downdraft hits the ground is more than 58 miles an hour. So a downburst is just when a strong downdraft rushes towards the ground and quickly rushes out. And this is the cause of most thunderstorm wind damage when combined with the winds aloft that these downdrafts can push towards the ground. So occasionally you can get winds and downbursts that briefly exceed 100 miles per hour. That is as strong as a pretty solid EF1 tornado. So certainly enough to do a good amount of damage. And if you've heard the term microburst before, that just describes a downburst that causes wind damage over an area that's less than 2.5 miles wide. A macroburst is just a wider, larger version of this, where the wind damage occurs over an area more than 2.5 miles wide. So when we get downbursts, they leave a very characteristic damage path because the air in a downburst is rushing out of a thunderstorm. So you can see that in the damage path when you get a downburst or a microburst, everything will be blown out kind of in one direction away from the middle of the thunderstorm where the downburst occurs. So, and that is, we'll get into this after the break, but that is kind of how you can tell if we have a downburst or a tornado. So just to kind of break this up a little bit, I don't have the most easy voice to listen to. We're going to give everyone a 5-minute break. It is 3:06 now, so at 3:11 we will come back and get through the rest of the presentation. That'll include a couple of case studies. We'll also talk about tornadoes. So at 3:11 I will be back and we will get through the rest of the presentation. All right, everybody, we're back and we're going to get through the remainder of this training here over the next 45 to 50 minutes. So moving on from hail and straight line winds to tornadoes. So a tornado is a rapidly rotating column of air in contact with the ground that is attached to a thunderstorm or a convective shower that isn't producing thunder and lightning. So this is a picture of a tornado here on the right, a very intense looking tornado. If we ever saw that here in our area, it would not be a good day. So luckily, most thunderstorms do not produce tornadoes. Only about 1 in 10,000 thunderstorms produce a tornado. And tornadoes, when they occur, they usually produce a very focused, relatively narrow area of damage, but that can be very intense damage. And the amount of wind damage does not necessarily indicate that there was a tornado or not, because again, as we discussed, sometimes straight line winds with a downburst can exceed 100 miles an hour, which is the equivalent of an EF1 tornado, which can do a pretty good amount of damage. So some terms related to tornadoes. We'll start with a wall cloud. So this is kind of like the first step on the way to potentially getting a tornado. A wall cloud is just a lowering, and it's a lot of times separated from the rain. A wall cloud just indicates that there is a very strong updraft going into a storm. So you can get a wall cloud with a non-rotating thunderstorm. It usually won't last that long, though. Once you get a rotating wall cloud, that is a sign that you have a supercell thunderstorm, so a rotating thunderstorm. And so that's kind of step one to getting a tornado, but it doesn't necessarily mean that you will get a tornado, but it's kind of like your first warning sign. So you know you have a wall cloud because it'll be relatively small, it'll be well-defined, and a lot of times you will see some rotation in a wall cloud. So, if you see something like this and it's rotating, you likely do have a wall cloud. So once you get from a wall cloud and you kind of move up to a funnel cloud, now we're getting closer to a tornado. So a funnel cloud is a quickly rotating funnel that's usually coming out of a wall cloud, but it's not quite to the ground yet. So the only difference between a funnel cloud and a tornado is on the ground and potentially doing damage. A funnel cloud is not quite there yet. So if you see a funnel cloud, it definitely is a warning sign that conditions are conducive for a tornado to try to form, potentially in the immediate future. So a telltale sign, we discussed this a lot more in the basic course, but a telltale sign that you're looking at a funnel cloud, a couple things. One, usually it is a smooth, well-defined feature, and two, it is spinning. Like you'll know it's spinning. Like if you were looking at, if this picture was a video, I bet you this funnel cloud would be spinning like a top. And once you get that funnel cloud in contact with the ground, then you have a tornado. And this is a picture from Jackson Township in Stark County from October of 2021. We had several tornadoes across our area that day. So going from a supercell to a tornado is a multi-step process. And we told you we were going to get a little more in depth on these things than we do in the basic course. And here we go right now. So to get a supercell off the bat, if you remember way back in the early portion of this talk, when we were talking about wind shear, the slide kind of had a picture of a horizontal roll. And that's what happens when you have wind shear, because you have the winds near the ground blowing at a relatively light speed, and then the winds aloft blowing at a relatively strong speed, and that kind of causes a rolling motion. And when you get an updraft, it actually tilts that horizontal rotation into the vertical. But that initial step only gives you a supercell, it doesn't give you a tornado. Once you get a supercell, you need to start getting some downdrafts, because that rain-cooled air causes a temperature difference, and it also causes a wind shift along the gust front. And that temperature difference and that wind shift actually causes the spin near the ground that can then produce a tornado. Once you get that spin near the ground, it needs to get ingested back into the thunderstorm to form a tornado. So it is a very tricky process, and this is why only 20% of rotating supercell thunderstorms go on to produce tornadoes, because you need all of this to happen. So we'll explain it a little better here, hopefully with pictures. Hopefully it's a very tricky process, so hopefully the pictures are a bit intuitive here. So, step one is you get that horizontal spin, or what we call streamwise vorticity near the ground. It gets pulled into a thunderstorm, and it becomes more vertical as it moves up through the thunderstorm, but it happens, well above the ground. We're talking 5,000 to 10,000 feet above the ground. So that's not your tornado. But what happens once you get rain and hail reaching the ground, you get that rain-cooled air next to the warm air getting pulled into the thunderstorm. That causes spin. And as that spin gets pulled into the storm, if it's successfully pulled back into the storm, that is when you get your tornado. So you get your tornado when the air getting pulled back in isn't too cold, and when the storm, the updraft itself, is strong enough to pull that air back into it. That's how you get your tornado. So sometimes you get all of this, but you don't get a tornado. You just kind of hang on to your rotating wall cloud. And this happens if the air getting pulled back into the thunderstorm is too cold, which means it's heavy and it can't get pulled back up, or if the thunderstorm itself just isn't strong enough to pull the air back in. And just to show you the supercell structure, again, to kind of help visualize what I'm talking about, where all that spin comes from, if you kind of picture, with the arrows, the wind in the air in both the forward flank and the rear flank downdraft, it's relatively cold, and it's blowing at a much different direction than the very warm and humid air getting pulled into the storm. And that creates a lot of spin along the two gust fronts that are represented with the cold front symbol on this diagram. And if the spin on those gust fronts is able to get pulled back into the updraft, that's when you get your tornado. So the most easy way for this to fail, I would say, is if the air in the downdrafts is just too cold. And what happens in that case is the downdraft surges out ahead of the updraft. It becomes what we call downdraft dominant or outflow dominant, and that makes it much harder to see a tornado develop. So tornadoes are tricky to form. A lot goes into it, but just to kind of test you mentally here, and I know I can't hear or see any of you, but I'm going to give you a few seconds to ponder if you think either of these pictures from Pennsylvania in October of 2018 are tornadoes or not. So I'll give you a few seconds. So the answer is neither one of these are tornadoes. The one on the left, it does look like a bit of a wall cloud, and maybe there is a small funnel extending out from it. So the one on the left is a situation where maybe it's on its way to becoming a tornado, but it's not a tornado yet, because that little, itty bitty funnel, if that is a funnel in the middle, it is not reaching the ground. So it's not a tornado. And then the one on the right is not really a funnel cloud at all, because if you remember what I was saying, if you're looking at a funnel cloud, it's going to be very smooth or laminar on its edges. This cloud is much rougher around its edges. So this one's tricky because, like the one on the left, it looks to me like it's coming out of a wall cloud. But it's not a tornado or a funnel cloud, it's just too rough. And what's more likely is it might just be a shelf cloud being looked at from the side, because you kind of have all that rain-cooled air behind and to the left of that cloud. So that might just kind of be a shelf cloud being looked at from the side. Now I'll give you a few more seconds to ask yourselves if you think either one of these are tornadoes. And the answer for both of them is yes, they are both tornadoes. And the way you can tell is especially the one on the left. It's definitely coming out of a wall cloud, and the wall cloud is so large it takes up almost the entire picture, but you can kind of see the edge of it there on the right-hand side. So it's coming out of a wall cloud. It's relatively smooth around its edges, and it extends towards the ground. So that is a tornado, and if you were looking at this, it would be clearly rotating. There wouldn't be any doubt. And same with the one on the right. That is trickier because it's just relatively small, but you note that there is a small, relatively smooth funnel coming out of that lowering that is a wall cloud, and it's extending towards the ground. Again, the contrast is poor in that picture, but that is a small tornado. And something like that is probably what a majority of our tornadoes locally look like, as opposed to those very, very large tornadoes that you might see out in the plains. So when we're looking at tornadoes on radar, or when we're looking at tornado producing storms, usually the rotation we see on radar is not the tornado itself, because unless you're very close to the radar beam, due to the curvature of the Earth and due to a very slight amount of tilt in the radar beam, the radar beam is scanning the storm, thousands of feet up. So we're just seeing the rotating updraft, or what we call the mesocyclone, as opposed to the tornado itself. And also the radar beam isn't fine enough, because the radar beam actually fans out the farther you get from the radar. It's not fine enough to truly sample the small circulation that exists in a tornado. So unless a tornado passes within, we're just talking a few miles of a radar, the rotation we see on radar is actually not the tornado itself. So this is a radar image of a tornado we had last summer along the Wayne and Holmes County border in July. It was an EF1 tornado, and on the right, that is what we call the radar velocity. The green air is blowing towards the radar, the greens, that's wind blowing towards the radar. The red is the wind blowing away from the radar. So clearly it's circulating or rotating pretty strongly, but this is just sampling the mesocyclone, or the rotating updraft in the storm, and not the tornado itself. But there was a tornado at this time. So what does tornado damage look like? So this is an example of tornado damage. This was the last EF2 tornado in our county warning area. It occurred in April of 2019 in Shelby, that is near Mansfield in Richland County. It was an EF2. And this is, very telltale tornado damage, because with straight line winds, the winds rush out and away from the thunderstorm, whereas with tornadoes, the damage is more convergent towards the tornado path. And you can kind of see with the arrows that the debris was blown towards the tornado path, and the debris was also dragged quite a distance. So that's a good example of tornado damage. And it did significant damage to some of those homes. Completely tore some roofs off them. And a lot of tornadoes in our area luckily are lower end. They can still be dangerous and damaging, but they're not as violent as what you can sometimes see in the plains or sometimes the deep south. But on occasion, we can get very strong tornadoes. So in June of 2010, near Toledo in Millbury, that's in Wood County, and it extended into Ottawa County, we had an EF4 tornado. Tornadoes are rated on a scale of 0 to 5, and once you get to a 4 or a 5, that's considered violent and very rare. So we had a very high-end tornado in our area a little over a decade ago, and that is a single-family home, or it was, right in front of where this picture was taken, and as you can see, completely destroyed. So even in our area, if conditions come together perfectly, it's not common, but we can get very intense tornadoes. We have a history of it. And then going back to the last really big tornado outbreak before that one in our area, it happened Veterans Day weekend in 2002, Van Wert, Ohio. that's just west of our forecast area, was hit by an F4. We had several other strong tornadoes in our area. One hit Tiffin and completely destroyed a number of homes. And one hit in Summit County, Macedonia, into Twinsburg, and that extended up towards Solon in Cuyahoga County. That was an F2 tornado. Back then we rated on the Fujita scale, so F instead of EF, but similar damage for the scale numbers. That was an F2 tornado, and this shows just how focused tornado damage can be, especially the Macedonia one, where that house in the middle was effectively destroyed, but the surrounding houses either weren't damaged or just had cosmetic damage, like siding getting ripped off. So tornadoes, they can produce very focused but very intense damage. So how do we tell tornado damage versus straight line wind damage? Because again, a weak tornado, quote unquote weak, and straight line winds, strong straight line winds, they can produce similar amounts of damage. With tornadoes, what we look for we kind of look for a chaotic damage pattern with, it's going to be generally convergent towards the middle of the path. That means damage will be generally blown towards the middle of the path, and near the middle of the path, you can get crisscrossing of damage, especially if you have a lot of trees, due to the winds on either side of the tornado being from opposite directions. So the damage, the way trees are blown down is a very telltale sign. When we survey damage, we try and determine if it's a tornado or not, and how trees are blown down or how crops are damaged is a very classic indication. And sometimes you can even see in crops the rotation in the damage pattern, and you can see that convergent damage path. And you could kind of see this in our Richland County case. It was still April, so the farm fields, the crops weren't growing yet, but you can kind of see in the debris pattern that generally convergent pattern towards the middle of the path. So moving on from thunderstorm hazards to how we predict them, computer models, help us out a lot. They help model the environment that might be in place, so that the computer models can kind of help clue us in ahead of time to how much instability we're looking at, how much wind shear we're looking at. They might tell us if there's lift, like a front moving in, and some of the higher resolution computer models can, make realistic looking predictions of thunderstorms. They're never 100% right. The classic quote, all models are wrong, but some are useful. No model is ever completely correct, but sometimes they can give us a pretty good idea. And I won't delve in too much to the alphabet soup on the model, but the HRR model is a short range model that updates every hour. So sometimes this can give us the best idea on the day of a thunderstorm threat of how it may play out, because it updates every hour, so it can take into account if it's raining ahead of the thunderstorms or how thunderstorms approaching the area are behaving. The NAM, NEST, and ARW, those are other what we call high resolution convective allowing models. They can simulate thunderstorms relatively accurately and give us a pretty good idea on how severe they may be. So a big difference between some of our computer models is their resolution, both horizontally and vertically. The very high resolution models are what we call convective allowing models, or again, we love our acronyms, CAMs for short. And those can simulate relatively realistic looking thunderstorms, but they're never going to be perfectly correct, but they can, again, give us a pretty good idea of what we're looking at. Lower resolution models, they cannot truly simulate thunderstorms. Their resolution isn't high enough, but they can still kind of tell us if certain ingredients will be in place. So again, we have all sorts of different computer models that are running through the day. Some of them run every hour, pardon me. Some of them run every 6 or 12 hours. Some of them update in, they simulate in 1 hour time steps. Some of them update in 15 minutes or simulate 15 minutes time steps, which when we're, thinking about how quickly thunderstorms can evolve, that those smaller time steps can really make a difference for us. And again, some models produce output that can look very realistic, like realistic radar. However, sometimes or very often those outputs are not precisely correct. They can give us an idea if the model is on the right track to how the day may play out, but they're never 100% correct. You know, if they show a tornado over one town but not another, it doesn't necessarily mean it's correct. So kind of take it with a grain of salt. So here is an example of a very high resolution forecast computer model. And again, it produces output that's very realistic looking, and in some days it gets the idea pretty correct, but it's never going to be 100% correct. So, you know, our efforts nowadays are focused on improving what goes into the model. You can kind of get it on this slide with the initialization, pardon me, and inputs. If the initialization and inputs are poor, the results will be poor, as they say, garbage in, garbage out. So, you know, efforts to improve modeling are focused on getting what's happening now correct, because you need to get that correct to properly forecast the future. Also, in terms of developing what we call ensembles, where that's kind of presenting us with different options among the models. So if all the models say one thing is going to happen, but then something else happens, you know, we're kind of caught off guard. Whereas an ensemble can present alternate scenarios. You know, maybe storms will develop at a different time, or maybe there will be rain in front of the thunderstorms or not. Or maybe thunderstorms will develop in one area instead of another. So an ensemble can give us a sense of the potential uncertainty. And as the day evolves, we can kind of clue in on which models or ideas are more correct and kind of lean on those ideas for the rest of the day. And an interesting point here at the bottom on model forecast of tornadoes. Tornadoes, as we kind of touched on, are very difficult to predict, very fickle and sensitive to a lot of different parameters. And some research done at Penn State by Dr. Paul Markowski, a very well-known name when it comes to tornado research, found that just making very slight changes to how rough the surface or the ground is can yield significant differences in terms of how strong a tornado is, or if a tornado even develops. So very, very, you know, at the moment, it's nearly impossible to model ahead of time if a tornado will truly develop or not. So we're gonna now look at a couple of case studies of severe weather events that happened across our area last spring and summer, and kind of show how all the ingredients went into producing those severe weather. And we'll also show some radar signatures of those events. So the event we're going to spend the most time on was last May 21st. This is what I would consider kind of a typical scattered severe weather day across our area. There were some damaging winds, some large hail. This was the day that produced the 2-inch hail in Geauga County we talked about a little bit earlier. So we're going to start aloft with the big picture. This is about 30,000 feet up. It is the 300 millibar pressure level, if you're familiar with that, or 300 hectopascals. So well up there. Sea level is roughly 1,000 millibars. It's that pressure level is sea level, approximately 1,000. So we're way up there in the upper levels of the atmosphere where the jet stream is. And the color fill is the wind aloft. The little lines with the flags or the with the flags or the lines attached to them, those are wind barbs. We discussed that a little bit earlier. Shows where the wind is coming from and how strong it is based on the number of lines and number of flags attached to it. And then the black lines, those contours are what we call isohypses, or lines of equal height. You don't really need to know what those mean. Just know that there is a ridge of high pressure centered off the mid-Atlantic coast and into the southeast. There is a trough where towards all those contours over the upper Midwest. So there is a trough approaching, which can act as a source of lift and maybe some wind shear. So that's kind of step one. We have a front, or not a front, my apologies. We have a trough approaching. So that's kind of step one. That gives us a bit of lift, and it starts giving us a bit of wind shear as some of that stronger wind aloft begins approaching. Moving on down, this is about 5,000 feet above the surface. It is the 850 millibar level. So getting closer to the surface, and the green lines, those are the dew points at that level. The red and the blue lines are temperature at that level. And again, we have in the kind of the light brown, those are the wind speed and direction. And the black lines, again, are the lines of equal height or isohypses. And the big thing that stands out at this level is there's a lot of moisture coming in from the southwest at this level into Ohio based on the much higher dew points developing there. And there's also a cold front moving in out of Michigan and Indiana. You can tell that by the very sharp gradient in the temperature and the dew points, and a wind shift from the southwest ahead of the front to more due westerly and even west northwesterly behind it. So we have a trough aloft approaching, and we have a cold front pushing in. So we already have some sources of lift. And now we're going to look at the Cape, the instability that we talked about earlier. So this is the mixed layer Cape. This is kind of the go-to for your summertime afternoon and evening thunderstorms, at least one of the go-tos for those types of thunderstorms. And we have a large pool of 2,000 to 3,000 mixed layer Cape across our area ahead of the cold front. So a pretty good amount of Cape. And now the blue color fill is what we call capping inhibition, or SIN. And that just means that there is a layer somewhere where air near the ground that's rising cannot punch through easily because there's a stable layer somewhere aloft. So that's what we call a cap. And if you'll note, there is a pretty good cap over Lake Erie and pushing into extreme northeast Ohio and northwestern Pennsylvania. That is because it's colder over the lake in May. The lake water is still, maybe 60 degrees as opposed to the 80s over land. And that creates a lake breeze of more stable and more capped air, and that is pushing inland. So, we have a couple sources for lift, and we have a lot of instability. This is your wind shear in that 0 to 6 kilometer layer that we discussed earlier, and a pretty good amount of wind shear. We're kind of on the edge of it. I would say 30 to 40 knots of wind shear is kind of a representative value across our area as that cold front pushed in out of northwest Ohio into north central, northeastern Ohio, and northwestern Pennsylvania. So, we have plenty of Cape, a fair amount of shear, definitely kind of in the area where multi-cell thunderstorms are going to be most favored, but maybe getting close to the point where there can be some supercells as well. So looking at a larger scale surface map and satellite image, so we have the cold front. That's that blue line with the triangles pushing in. This is a couple hours before the thunderstorms develop, so you can imagine that front is moving southeast into our area. There also is a lake breeze analyzed on this plot, that dashed gray line along the eastern Lake Erie shoreline. So that shows up pretty nicely. And this is satellite imagery behind the surface map. And you can see a lot of clouds over Illinois, Indiana, Michigan coming in from the west, but it's mostly sunny, especially over southern and eastern Ohio into Pennsylvania ahead of all of this. So we had a very warm air mass, humid air mass, and a lot of sunshine, giving us all that instability on May 21st. So a slightly closer look here at, a very, very clean hand-drawn image of the sources of lift that day. You had the big cold front coming in. You also had a lake breeze along the eastern lakeshore, and you can really see the wind direction change along the lakeshore. Like, for instance, at Cleveland Hopkins and at Ashtabula, we had southwest winds with temperatures in the upper 80s, but then at Erie, then at Lost Nation Airport there near Willoughby, at Avon Light, I believe that is that station just west of Cleveland, you had winds blowing straight off the lake with temperatures in the 60s. So a very sharp gradient there along the lake breeze. And there's also a very, very subtle boundary just west of Mansfield. You can note a very subtle wind shift there. So we had the big cold front, but we also had some subtle sources for lift in front of it. So as I mentioned, a lot of times the big question is, what is the source of lift that's going to actually cause our thunderstorms to develop? And on a day like this, where there were a lot of sources for lift, it can get kind of messy. So, quickly checking in before we dive in a little bit more, sources for lift include, definitely the cold front pushing in, definitely the lake breeze, and maybe that very subtle prefrontal trough and some of our higher terrain, especially near Mansfield and then maybe east of Cleveland. Those are all potential sources of lift near the surface. And then in the upper levels of the atmosphere, there was a trough approaching, which is a source for lift. There was a moderate amount of wind shear, definitely enough to get some organized thunderstorms and a pretty good amount of instability. So we're going to dive in a little bit more into some of the various threats in terms of wind and hail and tornado. But at the surface, plenty of ingredients seem to be in place. And obviously they were. We're not going to spend our time going over a case that didn't produce any severe weather with you. So this plot here, we talked very early on about what's called the lapse rate. That's how quickly the atmosphere cools with height. And the stronger or the higher the lapse rate, the more unstable the atmosphere is. So we talked about an elevated mixed layer, and that often presents itself in the mid-levels of the atmosphere, above about 8,000 or 9,000 feet above sea level, in the 700 millibar to 500 millibar range of the atmosphere. So again, that's above about 8,000 or 9,000 feet above our heads is where that elevated mixed layer that can come all the way from the Rockies and is a warning sign for some of our more significant severe weather events. So this plot shows the lapse rates in those mid-levels of the atmosphere between 700 and 500 millibars, and 500 millibars is about 18,000 feet aloft. And the lapse rates were between about 7 and 8 degrees Celsius per kilometer in that level, which is indicative of some amount of elevated mixed layer making it into our area. And then moving on to what we call downdraft cape. So we talked extensively earlier about how a lot of thunderstorm winds are the result of rain-cooled air rushing towards the ground and then spreading out and causing damaging winds when it hits the ground. And a way to measure how quickly these downdrafts might accelerate towards the ground is what we call downdraft cape. So regular cape is kind of a measure of how strong the updrafts may be. Downdraft cape is kind of the opposite. It tells you how strong the downdrafts may be. The stronger the downdraft cape, the quicker the downdrafts can rush towards the ground and the greater the potential for thunderstorm wind damage. So on this day, we had over 1,000 and up to 1,300 downdraft cape, which once you're getting over 1,000 or 1,100, give or take, that's some pretty strong downdraft cape, and that gets our attention. So on this day, on top of all that instability, a fair amount of shear, pretty good lapse rates in the mid-levels of the atmosphere, and a pretty good amount of downdraft cape. And then looking at the lapse rates again, this is in the lowest levels of the atmosphere. The lapse rates in the low levels of the atmosphere are a good indicator for how easily winds aloft can translate towards the surface. So the stronger the lapse rates in the low levels, the easier it tends to be to get damaging winds. And the low level lapse rates on this day were pretty strong, ranging from about 7.5 degrees Celsius per kilometer to up to 8.5 degrees Celsius per kilometer. So that's getting up there, and that makes it easier for strong thunderstorm winds to translate to the surface. So we discussed the amount of bulk shear. We had about 30 to 40 knots in place, which is starting to get to the point where supercells become possible, but not every supercell produces a tornado. And we talked earlier about winds turning and increasing in speed in the low levels of the atmosphere. And the more that happens, the more storm relative helicity we have. And once we get storm relative helicity of values approaching or exceeding 200, and the unit for that is meters squared per second squared, once that's approaching or exceeding 200, that's when our alarm bells for increased tornado potential really go off. And on this day, between 50 and 100 was most common, so maybe a little bit low for tornadoes. And the thing we look at when assessing tornado potential is what's called the LCL, or lifted condensation level. That basically means if you get air near the ground rising, when will clouds start forming? The higher this level, the drier the air near the surface is, and vice versa. The lower the level, the more humid the air near the surface is. And this helps inform us on tornado potential, because if the air near the surface is drier, the downdrafts tend to be colder, and that makes it harder for that air to get pulled back up into the thunderstorm. So on this day, the LCL heights were getting a bit high. They were kind of in the 1,000 to 1,500 meters above the ground range. So not necessarily high enough to 100% preclude tornadoes. I'd say once you get to about 2,000, that you can completely preclude tornadoes, but high enough that, it wasn't necessarily favorable. So kind of summing up the environment that day, the thermodynamics, as we call them, so that's the instability and the lapse rates and the downdraft cape, they were all pretty conducive for severe weather, especially damaging winds, and to some extent large hail as well, with those pretty strong lapse rates in the mid-levels of the atmosphere. The shear was strong enough to support some organization, 30 to 40 knots of shear, definitely enough to get some multi-cells, kind of on the fence for getting true supercells, rotating updrafts. But overall, the shear, especially the helicity, was a little bit weak for tornadoes. There were several different things that could potentially cause storms to develop. The main one was the cold front, but there was also a lake breeze and a prefrontal trough, and there wasn't really a cap to stop storms from developing. So when we get many different forcing mechanisms or triggers for storms, a lot of times we get what we call messy storms. And there was the upper level forcing ahead of the trough. It was somewhat weak, but there was enough that it helped cause some lift. So here was a very broad radar loop. So we had an initial cluster of storms go just north of Lake Erie this morning, and it produced severe weather in Canada. But then in our area, we had all sorts of storms develop in the afternoon. We'll let this loop through again. So after the first cluster kind of rides by just to our north, note how you get some storms forming on the lake breeze east of Cleveland. You get some storms forming on the prefrontal trough, not just west of Mansfield, and you also get storms firing along the cold front, closer to the I-75 corridor as well. And all of this happens pretty quickly, and we had a fair amount of severe weather this day, mainly in the form of damaging winds and large hail, but it was messy enough that we didn't get anything extremely high end like a derecho. You can kind of see how once we got a lot of storms, there was some competition going on, because storms, they want to pull in as much warm, humid, unstable air as they can. And once you get rain, cooled air rushing out of storms, that can kind of interfere with new storms trying to develop. And you can kind of see how it got messy through the radar loop. Most of these storms were multi-cells. They kind of organized into little lines or clusters. There were a couple of supercells early on that produced some hail. So here were the storm reports that day. The blue W's are wind damage reports. The green H's are large hail reports. And by large hail, I mean quarter-sized, 1 inch in diameter or larger. So we had a pretty good scattering across our area. And we had the most severe weather reports. 2 areas I want to clue you in on, or 3 areas. One is between Findlay and Mansfield. We had a pretty good swath of wind damage reports with a bit of hail. The second area to cue in on, we'll discuss all of these, is the hail east of Cleveland. And the third little area is from extreme eastern Ohio into northwestern Pennsylvania. There was a pretty organized little corridor of wind damage. So we'll look at all of these real quickly on radar. So this is a more kind of zoomed in, higher definition radar loop. On the left, you have your regular radar, and on your right, we have what's called velocity, how quickly the wind is blowing towards the radar in the greens and the blues, or away from the radar in the red. And you'll note that we had storms organized into a little line that actually was bowing out for a little bit there between the Findlay and New London area. And that is when we had the bulk of our wind damage in that area, was when that line was bowing out. But it started to get a little messy. The line began kind of running into the rain-cooled air from the thunderstorms early in the loop that developed and kind of moved through the Mansfield area. There's also a lake breeze evident. It's really hard to see, but on the left, you see a very fine line near Strongsville and Oberlin. That is the lake breeze. So you had storms kind of moving north of the lake breeze, which caused them to maybe begin weakening. So late in the loop, the storms began weakening, but there was a pretty good period there where we had a bow echo on reflectivity, a pretty good line with some pretty bright colors on the velocity on the right, indicating wind damage potential. And some of the wind damage was relatively significant, like damaged like gas station canopies and snapped some power poles and brought some trees down with this little line of storms. So that was a line of storms that kind of took full advantage of the shear and the downdraft cape and the instability. Next, we're going to look at a storm that produced hail this day that was 2 inches in diameter in Geauga County, east of Cleveland. So again, lines of thunderstorms tend to be our most prolific wind damage producers. Supercells tend to be our more prolific large hail producers. So this little storm was a supercell. It did not produce a tornado. And so a few reasons why. One, you can see on the reflectivity, it was a supercell. It had that characteristic shape and hook echo, but there was a fine line just ahead of it, and that was the storm's outflow boundary. And the outflow boundary rushing well ahead of the storm indicates that the outflow is cold and that it's going to have a hard time getting pulled back into a storm and producing a tornado. And you can see on the velocity on the upper right, you know, when we look for rotation, we look for reds next to greens. And we aren't really seeing that close to the ground here. So no real immediate rotation is evident near the ground. The bottom 2 are just kind of showing how tall the storm and how much rain and hail the radar is picking up aloft. And it was a very tall storm, about 50,000 feet tall. And it had a ton of rain and hail aloft, suggesting large hail potential. So this is the reflectivity on the left, or your standard radar on the left, and the velocity on the right. And this is just tilting up through the storm. And as you go up, you do see more characteristic rotation, reds next to greens in the mid-levels of the storm, indicating that it was a supercell, even though it didn't produce a tornado. And, but that helps explain why it produced the large hail. You can see once you get, starting really about 4,000 feet up, you start seeing some more coherent rotation, but that didn't translate to a tornado. And also on the left, you can see as you go up, just very, copious amounts of rain and large hail getting wafted into the upper reaches of the atmosphere, indicating a very strong storm. It didn't produce a tornado, but it produced some wind damage, some straight line wind damage, and some hail as large as 2 inches in diameter, which can do quite a bit of damage. So, this kind of shows the environmental analysis that we do, how important it was. You know, the environment told us a lot of instability, enough shear for maybe some, you know, supercellular organization, but it also told us that the downdrafts might be a little too cold for tornadoes, and also told us that the low level shear wasn't quite favorable enough for a good tornado setup. So that explains why we got a supercell that produced very large hail, 2 inches in diameter, but not a tornado. And here is a vertical cross section through the storm. And you know, that huge core of purples and pinks, you know, from the ground all the way up to more than 30,000 feet in the atmosphere, just shows how intense the storm was, that it was able to loft all that rain and hail to such a high altitude, and shows an updraft that was more than capable of producing some large to very large hail for our area that day. And then this is a cross section of the squall line that kind of took shape from extreme eastern Ohio into northwestern Pennsylvania. And this is kind of your characteristic, you know, multi-cell cluster. You'll note how, you know, updrafts develop and get taller, but then they kind of collapse, but then new updrafts develop. And as this initial updraft right here collapsed, that is when we had a pretty good amount of wind damage reported in southern Crawford County. This included a lot of trees that were snapped and some damage to things like carports and snapped power poles. So definitely a solid severe thunderstorm that produced a pretty good amount of wind. Now, I would, you know, I'm not going to spend as much time on this one, but I would be kind of, you know, wouldn't be doing it justice if I didn't briefly touch on the derecho that moved across our area, at least part of our area, last June. So this is a quick look at the upper levels with this one. And as you'll note, the jet stream in the color fill really was displaced to our north, which is common when we get those big clusters of thunderstorms in the summer. You know, they kind of occur on the very edge of the stronger winds aloft with the jet stream. But you can note a very, very subtle kink in these lines here coming out of Michigan and Indiana, and that was a very weak disturbance that helped spark the cluster of thunderstorms that turned into our derecho last summer. And here's a look at the satellite. So there was a stationary front draped across the area from Iowa, points east through Indiana, northern Ohio into Pennsylvania. That is where the derecho kind of tracked along. There was also a cluster of thunderstorms just ahead of the derecho over southern Ohio. We talked about that a little bit earlier. And this was the big thing that we had to figure out this day. Like, we knew there was a frontal boundary that storms were going to try and track along. We knew conditions were very favorable for damaging winds this day, but you know, we kind of needed to figure out where the clusters of thunderstorms would form and how they would kind of impact the environment and alter future clusters of thunderstorms. So very quickly, looking at the instability, the ML cape that was in place for the derecho, we had 1 to 2,000 in place across our area where the derecho tracked, and this analysis was at 10 o'clock at night. So this was a late evening severe threat. So the cape across our area was decent, but the cape just west of our area where the storms kind of initially developed was very, very strong. So that allowed the storms to really get a good head of steam coming into our area. And then there was enough instability or cape in our area for them to remain severe. These are the mid-level lapse rates. So this derecho last summer, it definitely had an elevated mixed layer. And that's something we look for our more prolific severe weather days in this area. You can get severe weather without an elevated mixed layer, but usually the worst events have an elevated mixed layer. And this event certainly did. Again, you know, 7 to 8 degrees Celsius per kilometer. That was the lapse rates over our area as the derecho tracked in. But just to the west, the lapse rates were even stronger. And that's where these thunderstorms really developed and got their head of steam. And then, you know, there was enough going for them environmentally that they survived across our area. D cape, downdraft cape, kind of a similar story. Certainly enough downdraft cape in our area for wind damage potential, but much stronger downdraft cape just to our west. And since that's where the storms really first developed and took on their organization, that's why they were so severe as they came through our area, because they really just had a lot of momentum coming in, and the environment in our area was supportive enough that once it started, it took quite a while for them to stop. And wind shear in the 0 to 6 kilometer layer, we had 40 to 50 knots solidly across our area, with more than 50 knots just to our west. So again, for this derecho last summer, the wind shear and the instability in the lapse rates aloft were certainly supportive of wind damage and severe weather, but they were extremely conducive just to our west, and that's really where the storms came from. So here's a radar loop of the derecho real quick. Again, regular radar, or reflectivity as we call it, on the left, and velocity on the right. And an important point here, the velocity looks like it weakens here kind of across the middle of our area. The storms did not weaken. That velocity is measuring the winds blowing towards or away from the radar. So if the wind is not blowing directly towards or away from the radar, we don't get a full look at the velocity. But note how this line took on a distinct bowing shape here as it moved across the Mansfield, Worcester, Mount Vernon area towards New Philadelphia, and it produced extensive wind damage in that area. And one more thing I'll point out as it loops through is very strong winds on velocity aloft coming in, and note how the radar reflectivity on the left weakens quite a bit behind the main line of storms as it pushes through our area. That is indicative of sinking motion. That's indicative of those very strong winds aloft descending towards the ground and into the line of thunderstorms. It's called a rear inflow jet in a derecho, and it goes to show that there was very damaging wind aloft getting pushed towards the ground in this cluster of thunderstorms. And these were the wind damage reports across our area, scattered wind damage across most of northwestern and north central Ohio, with much more widespread damage where that line really bowed out, where the strong winds aloft really made it to the ground, kind of in the Marion, Mansfield, Ashland, Worcester, Millersburg area. And there were 3 tornadoes, those red little tornado symbols. Supercells are the most prolific tornado producers, but very intense squall lines, they can produce, usually relatively brief tornadoes, and we saw that in this instance. So this produced a ton of wind damage. I would say it was easily the most damaging thunderstorm event we had in our forecast area last summer. Some areas were without power for about a week after this event, and in particular in Wayne and Holmes counties, where the line of storms really bowed out. There were many thousands of trees that were just snapped. Like, there were some areas where every tree was snapped. So, this was definitely a line of thunderstorms that produced tornado-like damage just from straight line winds. So where to get our forecast information? Our website is www.weather.gov/CLE. That is our homepage. The Storm Prediction Center's website, where they produce severe weather outlooks every day out to 8 days in the future. That is www.spc.noaa.gov. And the Weather Prediction Center, they produce forecasts or outlooks for flash flood potential over at the Weather Prediction Center. So, I'm guessing most of you have gone through the basic SKYWARN training, but we'll remind you real quickly of what to report and how to report it. Obviously we need to know where you are, what you're reporting, when it occurred, and who you are. So, if you're ever calling us or submitting a report on social media, we need all of this information. If you just tell us that it's really windy, that we can't do a whole lot with it. We need to know where it's windy, when it's windy, and if the wind is doing damage, stuff like that. Here's another graphic of kind of what's reported. So along with thunderstorm, wind damage, or hail, or things like funnel clouds and tornadoes, reporting flooding, if it's getting to the point where it's impacting yards, homes, or businesses, or is impassable on roadways because the water is too deep, that is enough flooding for you to go ahead and report it. And many different ways to report this information to us. I would say the quickest ways are via that unlisted phone number or on Facebook or Twitter. Those are the most immediate ways to get us reports, because if you call that phone number, it's going to ring our operations floor and someone will pick up the phone who is within a few feet of the people who are looking at radar and issuing the severe weather warnings. So that's an immediate way. And we also have people in severe weather situations consistently monitoring Facebook and Twitter, especially Twitter, for reports. So if you tweet at us or comment on a Facebook post, we will likely see it quickly. And Storm Clee is a great way to get us reports as well, but we don't check that as much in real time during severe weather. So if you have something you want to get to us right away, call us or submit it on social media. Maybe if you have pictures after the fact that you would like us to see or take a look at, that's when you maybe would send an email to Storm Clee. And also we have an extensive ham radio network across our area, and we work closely with these folks during severe weather situations. Volunteers will come into our office and relay reports that they are hearing from out in the field. So this is another vital way that we get reports in severe weather situations. So I am done. You are done with the advanced training course. Again, thank you for attending, and we appreciate any of you who are looking out for severe weather or flooding and reporting it to us. It's a very critical thing that you do that really helps improve the warnings we put out and really helps the public service, public safety that we provide. So I'm going to go ahead and stop the recording, and the presentation is over. And I'm not sure if this will be emailed out to all of you, but if you have any questions, please feel free to email us at the Storm Clee email. We will get to you as quickly as we can. Otherwise, we are done here, and I will see if we have any questions. So thank you for attending, and have a nice day.